So let's go ahead and demonstrate that property that we just discovered from the last theorem. I'm going to take this symmetric matrix, A is equal to 3, 4, 4, negative 3. Now for a 2 by 2 symmetric, it's only true that the 1, 2 and the 2, 1 entries have to be equal to each other. These two things can be anything. What we're going to show is that regardless of how I pick the eigenvectors, they are guaranteed to be orthogonal to each other. So first thing I'm going to do is set up the characteristic polynomial, and I'm going to say let's take the determinant of a minus lambda I, and then we'll set it equal to 0. So subtracting lambda from the two entries on the main diagonal, we get 3 minus lambda and negative 3 minus lambda. I always put those in first before I put in the 1, 2 and the 2, 1 entries to make sure that everything is spaced appropriately. Now, according to the definition of a determinant for a 2 by 2, that means I multiply the 1, 1 entry by the 2, 2 entry. So 3 minus lambda times negative 3 minus lambda minus 4 times 4. This is going to be equal to 0. If I FOIL this out and expand completely, I'm going to wind up with lambda squared minus 9. Then we'll have a minus 4 times 4. That'll be minus 16. This is still equal to 0. Combining like terms, I get lambda squared minus 25 is equal to 0. Now, as I frequently say at parties, when I go to parties, a difference of perfect squares factors into binomial conjugates. I like to push my glasses up my nose as I say that. Difference of perfect squares factors into binomial conjugate. We get lambda minus 5 and lambda plus 5 out of that, letting us know that lambda is equal to plus or minus 5. So with that in mind, we're going to come up with the corresponding eigenvectors by plugging them into the following. We'll say let V be equal to an eigenvector of the form V1, V2. So let's start with lambda equals positive 5. So we're going to set up that A minus 5i times V is equal to the 0 vector. That is to say, subtract 5 from each of the entries on the main diagonal. So 3 minus 5 and negative 3 minus 5. The 4's stay the same, and we augment with the 0 vector. First column represents coefficients of V1, and second column represents coefficients of V2. If I simplify what's inside here, this will be negative 2, 4, 4, and negative 8. The observation that I'm going to make here is that these two rows are now multiples of each other. Because they're multiples of each other, I can use an elementary row operation of 2 times the first row and add to the second row, and that'll give us a row of zeros. I am going to shortcut this though and say we'll put this into reduced row echelon form. We'll get that row of zeros in the second row, that's guaranteed. And the way that we can get that leading 1 in the first row is dividing the first row by negative 2. So we'll get 1, negative 2, 0. To interpret this as an equation, this lets me know that V1 minus 2 V2 is equal to 0. So what I'm going to say is let our eigenvector be equal to, I'm going to let V2 be equal to 1 for our free variable. If I plug in V2 equals 1, we'll get V1 minus 2 is equal to 0, therefore V1 would have to be equal to 2. Now, any multiple of this would still be considered an eigenvector and would still work out okay. Now, let's check to see what we get for lambda equals negative 5. For lambda equals negative 5, we're going to see A minus negative 5 times I, so A plus 5i times V is equal to 0. So we'll be adding 5 to each of the entries on the main diagonal from before, and that'll be 3 plus 5, 4, 4, and negative 3 plus 5. Augment with the 0 vector, and we good. Now again, this represents coefficients of V1, this represents coefficients of V2. Simplifying each of these, we'll get 8, 4, 4, and 2. Once again, augmented with the 0 vector. Once again, these two rows happen to be multiples of each other, which means that I can take negative 1/2 of the first row and add it to the second row, and it will 0 out. Once again, though, I'm going to shortcut this to say we'll take this to reduced row echelon form, Negative 1/2 of the first row add to the second row will wind up giving us a row of zeros, which is to be expected in the eigenvector eigenvalue problem. Then I can take my first row and divide by 8 to wind up with the leading 1 that we desire. Interpreting this first row lets me know that v1 plus half of v2 is equal to 0. Now with that in mind, our free variable is v2, but with that in mind, I want to make sure that it's an even value so that we wind up canceling out this fraction of 1/2. So arbitrarily, I'm going to pick 2 for it. Now when we pick 2 for this, we get that v1 plus 1 is equal to 0, therefore v1 would have to be negative 1. Now according to the previous theorem, these two vectors should be orthogonal to each other. Let's check that. So check for orthogonality. And that'll be 2, 1 dotted with negative 1, 2. A quick dot product lets us know that these are, in fact, orthogonal to each other. Now, this is regardless of how I would have chosen the free variables. The only thing that that has an impact on is how long the vector is. Now, the big important picture that we get out of this is out of the Gram-Schmidt orthonormalization process, as long as your eigenvalues are distinct from each other, it is not necessary for us to apply the Gram-Schmidt orthonormalization process. Rather, we can just take each of these vectors and turn them into unit vectors, and that's how we get our matrix P.